Consider a function that has this generic shape. It suggests that as the independent value increases, the dependent value decreases, bottoms out, and then increases again. What about this graph? It suggests that as the independent values increase, the dependent values increase, peak, and then decrease again. Graphs like these might represent the cost to make a container of a given volume based on its width, or it might represent the number of gifts that you can wrap with a roll of paper based on the size of the packages. In general, the turning points on these graphs are of interest to engineers and economists as they represent the ideal value of the independent variable in order to optimize the y variable. The general technique used to solve these problems has just two steps. You must be able to write your dependent variable in terms of just one independent variable. That can be trickier than it sounds. The volume of a box, for example, depends on three variables: length, width, and height. To get it to be dependent on just one of these variables, you must set constraints on the other two. Usually, reconciling these constraints involves algebraic manipulation of simultaneous equations. Once you have your function, it's easy to find the optimal x value. The turning point, by definition, has a slope of 0. If we take the derivative of the function and set it equal to 0, we can solve for the x values where the turning points occur. Let's check out an example. Find a pair of positive numbers that add up to 9, which have the largest possible product when one is multiplied by the square of the other. First, we have to write out the mathematical statements that represent the situation. These are our constraints. Let's say that the two numbers we want to find are x and y. They must add up to 9. X plus y equals 9. The product of one and the square of the other is what we want to maximize. P equals x times y squared. We only want p to be a function of x. Let's get rid of the y with some algebra. We can rearrange to say that y equals 9 minus x, so then we can rewrite p as x times the quantity 9 minus x squared. As you can see, this function is cubic. We can simplify it like this. Now, what we're really interested in is the turning point where the product is maximum. This is easily accomplished by setting the derivative of p equal to 0 and solving for x. These x values will correspond to the places where the original function's slopes are 0. The derivative of a cubic becomes a quadratic, of course. We can use the quadratic formula to find the x values where this function is equal to 0. The values for our coefficients are 3, -36, and 81. Doing the arithmetic provides two answers, 3 and 9. How do we choose which one is correct? In the premise of the question, it said both numbers were positive and added up to 9. Therefore, one of the original numbers can't be 9. Let's do a quick check on our answer. If we assume that x is 3, then y is 6, and their product is 108. For comparison, if x was 2, then y would be 7, and their product is 98. Yet again, if x was 4, then y would be 5, and their product is 100. Based on this pattern, it does look like our technique did produce the values with the highest product.